now class officially begins. How about that? All right. Okay, on the agenda for today. So in the lecture notes, the two readings for today were sections 3.3 and 4.0. If you read 3.3, you're probably thinking, what the hell? And so I think it makes a whole heck of a lot of sense. Really, if you think about it, the only reason for having 3.3 done is to understand a key step at the end of 4.0. So I'm going to introduce it the other way around. Start out with 4.0, and then come back to 3.3. And the reason is, have you ever had these? It's almost in the current linear form. It's almost like those math. Have you ever had a math instructor who is like starts out with a central tenet and then moves down, and then you have no idea where she's going with it, and then finally there's this like conclusion that makes total sense. But you had no idea why you were doing anything you were doing until you got to that point? Yeah. So before talking about anything in 3.3, we're going to write out what the final conclusion is going to be and why it's relevant, and then go through the math behind it. So that's the rationale and sort of moving around between those two different sections. Okay, so we're going to start with 4.0, which and that leads to confidence intervals, which are hugely important in statistical testing. So let's start. Just out of the way, actually. I'm going to stand today. Wait. All right. Come on, do something here. There we go. Nice empty sheet. Okay, cumulative density function. And not surprisingly, we call it the CDF. Wow. And we call the PDF the probability density function. So hopefully you can see that there's a connection there in terms of our use of terminology. All right. At any rate, what is the CDF? It's the integral over the PDF. And we're going to indicate it by a capital F of M to discriminate it from the probability density function, which has a lowercase notation. So capital F of M is the integral from -infinity to M of f of x dx, where f of x is the PDF. So let's just consider a Gaussian distribution. What do we expect f of m to do? Let's look at some of the limiting values. What is the value of f of m going to be at -infinity? 0. What is the value of m of f going to be at positive infinity?
1.
Why 1?
Because we normalize our...
Because we have a normalized PDF. Excellent. Yeah, great. Fantastic. Okay. What's it going to be at 0? 0.5. Yeah. So we know if we have 1 here and 0.5 there, that it's going to, I'm sorry, m at 0, it's going to look, boy, that's really terrible. Let's just do that over again. Oh, come on. Can I do Control Z? I thought I could. Okay, fine. There. That's better. And asymptotes to 1, roughly. The functional form of this is, kind of stupid. In the sense that it's a Gaussian, it's an integral over a Gaussian. There is no analytical solution for an indefinite integral of a Gaussian function. So we just have to evaluate it numerically. So in this case, if f of x is Gaussian, then you end up with capital F is just the integral from -infinity to m of 1 over 2 pi sigma squared e to the minus x squared over 2 sigma squared. And I've left out the minus mu because mu is 0 here, as shown. And there's another, oh yeah, dx. Sorry. Now it's official. All right. So there's nothing we can do to simplify it. That just is the definition of the CDF, and so we'll forge on with that as our functional form for the PDF, for the CDF. Okay, everyone okay with this? Excellent. Can I move on to the new slide? I see a couple people still writing. I'll give you a minute or two. Not a whole minute or two, like 3 seconds. All right. Confidence intervals. And the z-statistic. That's the next topic. We're going to start out talking about what the z-statistic is and why it's useful. And then finally what confidence intervals are. So let's consider a Gaussian distribution, or a normal distribution. Yes?
Is this capital F or lowercase f?
Lowercase f.
Okay.
I'll typically, because I often my capital F's look a whole heck of a lot like my lowercase f's. I'll try to do a very good job of discriminating it based on x versus m. But always ask for clarification if there's any confusion. Okay, so this is a standard Gaussian distribution, right? If we want to talk about a confidence interval, we'll do confidence intervals first and then go back. I think I said I was going to do it the other way around, but I lied. We're talking about confidence intervals first and then go back and introduce the z-statistic. So the confidence interval, if this is your Gaussian distribution centered around mu, we're going to define the confidence interval to be something where some fraction of the total probability density lies within this range. If I want 100% of the probability density to lie within a range, that range has to extend from negative infinity to infinity, which is a really just inconvenient set of limits to use in practice. So we have to define some realistic finite range, and that's based on the assumption that we can capture some finite probability density within it. And so if we want to have 0.95 of the total, so 95% of the total probability. Lying within this range, x min to x max, where this is x min and this is x max. Then 95. We could also, if we wanted to do 99 percentile, then we're going to have a slightly bigger window, right? So we want 75 percentile, 60. We can decide this for any particular confidence interval that we want, right? This is just one example. One annoying thing, though, is that if this is my Gaussian distribution, I have to, for every new Gaussian distribution, I have to recalculate what a new value for x min and x max are going to be. Right? I can't come up with a universal solution for this because I've got 3 parameters that change every time I'm considering a new Gaussian distribution, x, mu, and sigma. Make sense? So yes, this is a very useful criterion in terms of this is going to be an integral over the cumulative density function too. Hopefully you can see that. What this is really saying is that 0.95 is going to be the integral from x min to x max of f of x dx, right? That's the total probability is going to fall within that window is what we're really saying. And we haven't really explicitly stated this, but we're also assuming the window is symmetric about the mean. And that'll show up really nicely when we get to the z-statistic. We're implicitly assuming that right now. So, okay, so for Gaussian distribution, if we want to come up with a general way of looking at any Gaussian function and finding that same range, we're going to make a substitution to the z-statistic. Okay, so let's consider, is it okay to move on? Questions? No, fantastic. So, okay, so let's consider the substitution. Z is defined to be x minus mu over sigma. If that's f of x, then what is f of z? Is 1 over the square root of 2 pi sigma squared sub z e to the minus z squared over 2. Hopefully everyone can see that. It's really, that is z squared, making the substitution. If I have a Gaussian distribution with a mean of 0 and a standard deviation of 1, which is implied by that numerator there, what is, well, I just told you, what is sigma squared sub z? Sorry?
1.
Yeah, I just said it. 2 of you were listening. No, I take it back. That's mean. That's mean. 2 of you were bold enough to feel confident in what I said to repeat it to me. Yes, that's exactly right. So it turns out that sigma squared z is simply 1 because of the form of the numerator in this case. So this whole thing just boils down to 1 over the square root of 2 pi e to the minus z squared over 2. So by making this substitution, we now have all Gaussian distributions describable in terms of z. In terms of the general z parameter, which is equivalent to a Gaussian distribution centered at 0 with a standard deviation of 1. Why is that useful? Not meant to be a rhetorical question. I really am open to answers here. Why do you think we go through this trouble? What's the advantage of having a universal definition for a Gaussian function? Yes?
All your parameters don't change every time?
Yeah. What was the pain in the ass part about not having a universal thing? That we have to reevaluate what x min and x max are every time we have a new Gaussian function. But if I have something that is written in terms of this generic variable that applies for all Gaussian functions, we can now define confidence intervals with respect to z, and then substitute in the particular values of mu and sigma for any individual distribution to see what those corresponding limits are going to be in the specific case. So we now have to, the reason this is useful is that we are often evaluating these things numerically. And so now, this predates when computers could do this far better than anything else. And you had to look all of these things up in honest to goodness tables. And I know it's hard to imagine, isn't it? There'd be actually a paper copy with tables of numbers that you'd have to reference. I'm sure I'm glad we don't live in those days anymore, right? But at any rate, I think that this is part of why it's sort of nice to have these. Well, I digress. Okay, back on point. By having the z statistic, it's a nice universal way of describing all Gaussian functions in a single parameter, and we can now talk about confidence intervals in terms of z, and then substitute those in for any particular Gaussian distribution and know what they would correspond to for a particular measurement. We'll look at now lists of confidence intervals. And we'll start out with double-sided. Z. Probability. Come on. That doesn't look like anything like probability. That looks like PRDO. I don't know what the heck I was writing there. There we go. Probability. All right, so if we take, for example, I'm not going to remember the numbers here. Well, I know a couple of them off the top of my head. How about that? One of them is if the probability is 0.95, well, it's 3 points. We'll just make one of them. 0.95, that corresponds to a z-min of 1.96. So that would be 1, 2, 95% of the probability falls between this negative 1.96 to 1.96 window.
It's not showing.
Yeah.
Give it time. Here, everyone just gather around my screen. How you doing? Okay, let's try this. It's disconnecting. Lovely. Sometimes you need a reboot. When my adapter gets too hot, it starts to
If the z distribution is centered at 0, why is the z minimum greater than 0?
So the question is, if you've got a z statistic, well, I can always go back to the old school way. If you have a z distribution centered at 0, then why is the minimum not 0?
Not less than 0. Because if it's...
Yeah, it is.
Oh, okay.
Okay, if now it's ready to connect, let's see if it'll actually connect. Hey, okay. Plus or minus. How about that? Okay, excellent. We'll see how long this lasts. All right, and I also know that 0.94 or 954, I think that's what it is plus or minus 2. Well, I mean, that's pretty much what we use because, 1.96 and 2, they're pretty darn close. So usually if we want a 95% confidence interval, we'll use 2 sigma. Maybe that sounds familiar to some of you, maybe it doesn't. For those of you that it does, then yay. I think there's another couple numbers in here that are in the lecture notes that are nice compliments. Okay, yeah, so there's this is basically a rehash of what I was just saying. For the 95%, it's between negative 1.96 and plus 1.96, and then you can go up from there in terms of the how much you're capturing. Now you see you get rapidly diminishing returns, right? Because if you go from 95 to 99, well, actually to go from 1 to 2, when you go from 1 to 2, you gain a lot of additional contribution, right? It goes from 70 to 95. You're getting like 25, 27% of the total probability density goes out by another standard deviation. If you got another standard deviation, you go from 95 to 99, that's another 5%. So you go from 25%, and then you only have another 5% increment by going out an additional sigma. If you got an additional sigma, the most you could possibly get is another 0.3%. And so it really starts to drop off very rapidly, and that makes sense because you have a Gaussian distribution. It's going to drop off rapidly in the wings. And so there's not a whole lot of probability density once you get out there beyond 4 sigma, 3 or 4 sigma. Okay. So that is all well and good. What was my next topic?
Pretty sure it was the experimental standard deviation.
Yes. Any questions on this before I move on? Easy stuff. Clear. Not like section 3.3. All right. The next part is what happens. Oh, I should mention one more thing before I do this. I'm sorry. Let's do single-sided versus double-sided. Consider an experiment to test water quality where the maximum concentration of lead could not exceed 1 part per billion. It's 1 plus, I think, right? No one's disagreeing, so I'm going to assume that it's correct. All right. I'm sorry? I don't know. That's why I asked. 2 plus? Okay, we had one person nod 1 plus, and no one else responded. Okay, we'll put a plus or 2 or 1.
It's 2 or 4, yeah. 2 or 4. It's not 1. It's not 1.
This is why I'm not an inorganic chemist, right? That's PbCl2 2 minus, right? Okay. Yeah, not today. Hopefully, man. That's some scary stuff. Man, need for analytical chemistry there, huh? Okay, so if we're designing, if we're testing, and let's say we know from this test, we've done this test enough times that we know the experimental, we know the true variance in the measurement. We know sigma from many similar measurements. And is a particular measurement of water quality within or without that 95% of the anticipated value? Is a particular measurement statistically significant in terms of the amount of lead identified? I decided to make it 2 minus this time just to throw you guys off. Okay, fine. So what are we really asking here? We're saying if I've got some known variance in the measurement, I've got some value, and I'm asking, is the lead, if this is my measured value, is the lead concentration, I'm not explaining it well. When we get to actual hypothesis testing, it'll be easier to see. But I just want to introduce the fact that there is a single-sided versus double-sided. So maybe this example is a little too far beyond what I want to do right now. I guess the key point is that for many measurements, you don't care if it's above or below. You only care about if it's one way or the other. And maybe this plot here is actually making things worse instead of better. So let's just pretend it doesn't exist and go back to the problem. This is just one example where you would not use a double-sided assessment because you don't care if it's less than the limit. You only care if it exceeds the limit with statistical significance. Does that make sense? And so your test is really only on one side. It's only from this value to positive infinity. You're not asking, is it below some limit as well? And so this is why you can use the same set of tables to describe both single side and double side depending on how you view the limits and how you use the limits. And you'll see an example of that later on. I'm just planting the seed right now in terms of what sort of scenarios would result in a double-sided limit versus a single-sided limit. Is that clear? Move on? Okay. Now we'll ask the question, what happens if you use the experimental mean and standard deviation instead of a true mean and standard deviation? So if sigma is known a priori, let's consider that case first, and then we'll make a substitution for our estimate for sigma. Then the distribution about the mean for an average, for a mean. Oh, here we go, a mean of n measurements. How about that? If mu is x bar plus or minus the magnitude of z times sigma over square root n. Where does that come from? Well, that plus or minus is just meant to indicate that you have some spread, just like a Gaussian. That might be normally distributed, it might be otherwise distributed. But if we're assuming it's normal, then this plus or minus is the range, that you have. The uncertainty might be some. If you have like 95% confidence, then you can calculate what that plus or minus window should be, for example. But in the generic sense, it is some window, and your mean is the true mean is going to be given by x bar plus or minus this range. The square root of n. Where does the square root of n come from? Well, if we were not doing an average, then the spread in those x values would be sigma. If we're now doing an average, then the spread in the mean is sigma divided by root n. So that's where that sigma over root n comes in. That's the variance of the mean, well, the standard deviation of the mean. Make sense? Okay, so this is really just saying mu is roughly, the experimental mean plus or minus of the standard deviation, the true standard deviation of the sum, of the mean, rather, if we're dividing by n. All right, and then you can rearrange this to solve for z by, let's see, if we subtract x bar from both sides, that's going to be, we're going to multiply by the square root n over sigma times mu minus x bar, right? Something like that. Yeah. There's a question. A whispered question.
Yeah, if that's plus or minus, why do you have?
We'll make this magnitude. How about that? Okay, I'm going to keep my red pen, though, because I want to discriminate that between the analogous measurement, the analogous expression, if I don't know sigma, but estimate it from S. So if S is the experimental standard deviation, then I introduce this new parameter t, which serves the same role as z. Right? So t and z are tied, and sigma and s are tied. And just like I solved for z, you could solve for t, and what you get for t, it's going to be mu minus x bar, still put the magnitude in there. And then now it's going to be S divided by the square root n. Oh, and it's magnitude. Everyone feel okay with this substitution? So I don't really know anything about t just yet. But I know it's going to be analogous to z, but when using the experimental standard deviation instead of the true standard deviation. Yeah?
Can you just write t in the exact same form that you wrote z?
Yeah. Yeah, I just put the n in the denominator, but it would be, if you like that more, then let's do that way. It's less. No. I'm just, I like to make things more confusing than they need to be. We'll write it here. We'll even make it all exactly the same. So the square root n over s times mu minus x bar. Okay, there we go. So no big change, except now we have this new parameter t instead of our nice normalized, understandable. Everyone was crystal clear on what z is doing, and now it's not exactly sure. We're hopefully not feeling totally comfortable with t. Hopefully you're not feeling totally comfortable with it yet, because I've been sort of alluding to the fact that it's not exactly z, right? And why is it not? So then the next question is, what is the PDF of t? And why do we need to know it? Well, okay, maybe. I think I know where you're going, but let me ask this. How did we define confidence intervals about z? Well, by integrating over the PDF. We defined confidence intervals by integrating over the PDF of z. So how do we find confidence intervals using the t statistic? Exactly. Exact same thing. We're going to have to integrate over the PDF of t. To generate experimental confidence intervals. We must similarly integrate over the PDF of t. Which goes back to my initial question, what is the probability density function for t? Well, okay, we have t equals x bar minus mu, magnitude, over s times square root, well, divided by square root n, right? I'm now going to go ahead and rewrite it the way I wanted to that first time. Let's start out with that one. What's the PDF of X bar? Assuming X is normally distributed. Yeah. I heard a mumble over here. You guys are really keen on this mumbling. If I mumble it, maybe I won't have to raise my hand. If I mumble it loud enough, won't know where it came from, but he'll just move on. Yes, exactly. The PDF in X bar is normally distributed if the PDF in X is normally distributed. Oh, I'll switch inks. What is the PDF in S? Oh, I can fix that one. Good. I thought it was actually a network adapter, a wireless adapter. Yeah. Will it be normally distributed? I don't know. Let's find out. What is S again? Yeah, so S is 1 over n summation of xi sub I minus x bar squared, right? And we are now safely in the throes of 3.3. And in the interest of time, I'm going to outline it here and then turn the floor over and then pick it up again on Thursday. Well, actually, I guess we have questions on Thursday, so we'll pick it up again the following week. So I'm just going to sort of lay out what the framework is going to be for evaluating this problem. And then we'll come back to it when we want to get when we actually start building in that T statistic table. Okay, so this is again section 3.3. How are we going to approach this? The first step is going to ask what is the PDF of x minus x bar? And our answer is going to be normally distributed. Second one, what is the PDF of x minus x bar squared? Right? Or d squared, the deviations. I'll put my little eyes in there. Yeah, this will turn out to be a gamma distribution. And then what is the PDF of a sum of squared deviations? And then the answer for this will turn out to also be a gamma distribution. Oh, and this is squared. And then the next one, we'll just rescale it by n, so I'm not going to worry about that one. And then what is the PDF of the square root of the sum of squares, of the sum of square deviations? And this turns out to be, it turns out to have the form of a moment of a normal distribution. So it would be the normal distribution multiplied by x to some polynomial. It'd be x to the, what do I want to put here? Some little n times normal. And then finally, what? Oh, it won't let me do it. You're going to let me do it. You have to let me do it. PDF of t equals x bar minus mu over s, well, times the square root n over s. And then finally, after we've answered question 5, we can then evaluate the limits of integration for defining a probability density, a finite probability for a confidence interval in T. We have to go through this entire process. So it would be so nice if S was just normally distributed, because then we wouldn't have to do any of this and life would be grand. Unfortunately, it is not. And so it turns out to be a lot of additional pain to get the right result numerically from something that, that would otherwise be relatively straightforward to evaluate. There's a question?
Yeah, for number 4, when you say x to the n times normal,
Yeah.
would that be the same thing as a Gaussian not centered on 0?
That's a great question. So the question is, if I have a Gaussian function and I'm scaling it by some x to a power, is that the same thing as shifting it? And the answer is no, because if I'm just going to let's write a Gaussian is equal to some constant times e to the minus x minus mu over 2 sigma squared. That's a Gaussian distribution, right? What we will find out is that once we go through this whole process, the moments of s squared, I think it's s, no, the moments of s are going to have the functional form of, let's see, what do I want to call it here? Instead of g, we'll call it f. It's supposed to be an x, by the way, not a y. Some new constant. There will be x to the n, e to the minus x minus mu squared over 2 sigma squared. And that, because of the exponent, because of the e, there's really no way to put this into there. And that's why I say it looks like a moment of a Gaussian distribution. Because if you were to calculate what is the average value of x squared given a Gaussian distribution, you would calculate x squared times g of x f, or dx. That is f of x. Right? That would be how you would calculate the second moment of the Gaussian distribution. And so it has sort of the same functional form where we're going to have these things that have x to some powers inside the actual PDF now. Does that help clarify? Okay, great. Other questions on this fun stuff? Awesome. Well, then I will turn the floor over to my esteemed colleague. You're probably going to need to use this one, aren't you?
Yeah.
You want to use, how do you want to connect in?